Hi, today I'm going to talk about improved product-based high-dimensional expanders. Here's an overview. So a high-dimensional expander is a generalization of an expander graph to hypergraphs. Now there's only a few known constructions of high-dimensional expanders, and in particular, a randomly chosen hypergraph will not be a good high-dimensional expander with high probability. This is in contrast to the low-dimensional case, where a random graph is a good expander with high probability. This makes a construction by Lu, Mohanty, and Yang from 2020 very interesting, as they gave a very elementary construction, essentially consisting of a high-dimensional version of a tensor product, for high-dimensional expanders of all dimensions, but it did have a suboptimal high-dimensional spectral gap. So in this work, I'll introduce a modification of the LMY construction with an exponential improvement in the spectral gap in high dimensions. Now to motivate this work, you may recall that there's many uses of expander graphs throughout CS and theoretical CS. And recently, there's been more interest and more applications of high-dimensional expanders. Just to list a few examples, there's been some surprising and interesting applications to complexity theory, specifically to agreement tests, to sampling, to coding theory or to list decoding, and to quantum computing or to quantum codes. This list isn't meant to be comprehensive, but the basic idea here is that there's been a number of recent interesting applications of high-dimensional expanders. And this makes it all the more interesting that we only know a couple constructions of optimal high-dimensional expanders. And the optimal constructions, at least to the best of my knowledge that we know of, are algebraic and fairly non-elementary. They're fairly involved to analyze, or at least significantly more involved than the construction I'll be looking at here. So the question I'm trying to ask is, how far can combinatorial techniques take us? How well can we do with an elementary construction? Asking this question has led to new insights and new results in the past in other areas. For instance, just to give a couple examples, the zigzag product, which was used for combinatorial constructions of expander graphs, then led to showing that SL equals L, or solving undirected ST connectivity in log space. And another example is Dinur's proof of the PCP theorem, which made progress in an area that had previously used more algebraic techniques. So to define a high-dimensional expander, as I mentioned, it's a generalization of expander graphs to hypergraphs, and we'll actually restrict to a particular type of hypergraph called a simplicial complex. So this is just a hypergraph where the edges are downward, the hyperedges are downward closed, meaning that if we have any hyperface sigma, which we'll call a face, so any face in our simplicial complex, then all subsets of that face, all subsets of that hyperedge, also belong to the simplicial complex. So here's an example. We say that the dimension of a face is one less than the number of vertices. So here's a vertex or a zero-dimensional face, an edge or a one-dimensional face, and a triangle or a set of three vertices is a two-dimensional face. And because this is the highest dimension of any face in the simplicial complex, we say that the simplicial complex X has dimension 2. Now there's a few different non-equivalent notions of high-dimensional expanders. The one I'll use here is based on the k-dimensional up-down walk from Kaufman and Mass in 2017. So this is a fairly natural generalization of the notion of expander graphs, which require a spectral gap in the random walk on the vertices. Here we're going to define a high-dimensional random walk called the up-down walk and require that it has a spectral gap in all dimensions. So the k-dimensional up-down walk, it's a random walk on the k-dimensional faces, and it's fairly natural. So here I've drawn the one-dimensional case. So we start at an edge or a one-dimensional face, and the up-down walk just consists of repeatedly adding a vertex in up step or dropping off a vertex in a down step. So we just repeatedly add and drop. And the up step, both of these steps are random. The up step has probabilities proportional to face weights. So we'll be dealing with weighted complexes, just as we can have weighted graphs. And the down step will just choose a uniformly random vertex to draw. Now again, paralleling the study of expander graphs, where we'll typically look for a family, an infinite family of expanders. Here we want to construct infinite families of high-dimensional expanders. So what this means is we want to construct an infinite sequence of simplicial complexes such that as the number of vertices goes to infinity, we have a constant dimension h, and then we have bounded degree, so a bounded number of faces containing any vertex, and we have a bounded spectral gap. So the spectral gap of all k-dimensional up-down walks is bounded below by a constant. Now, where we'll differ from the study of expander graphs is in the parameters we're trying to optimize. You may recall that for expander graphs, for instance, Ramanujan graphs, the optimal expanders optimize the spectral gap as a function of degree. Here we're not so focused with the exact value of the degree as long as it's bounded. And instead we want to optimize spectral gap as a function of dimension k. So in each dimension k we ask, what's the largest possible spectral gap we can guarantee? And it turns out that the optimal high dimensional expander has a k-dimensional spectral gap for the up-down walk of around 1 over k. Here I've outlined some prior work on high-dimensional expanders. So these first two constructions of high-dimensional expanders give an optimal spectral gap for the k-dimensional up-down walk in all dimensions k. The first is Ramanujan complexes, which were shown to have an optimal up-down walk spectral gap by Deneur and Kaufman in 2017. And then 2020, Kaufman-Oppenheim gave a construction based on coset geometries that was also optimal. Now, the second construction is significantly more elementary than Ramanujan complexes, but both of these are still algebraic and somewhat involved to analyze, or at least they're significantly less elementary than the analysis of the construction that I'll look at, which is a modification of the LMY construction. This is purely combinatorial. It's essentially a higher dimensional graph product, and it is unfortunately not optimal. So the spectral gap in dimension k is on the order of 1 over k times 2 to the k. That was a bound shown by 11 Lau. Now there have been some other papers on combinatorial constructions of high dimensional expanders, but to the best of my knowledge, these haven't given quite what we want. So CLP had a combinatorial construction in the 2-dimensional case, whereas we want constructions of all dimensions. And then Conlin, Tidor, and Zhao gave a construction from Cayley graphs, but the groups they used for these Cayley graphs were abelian, so it did not quite have bounded degree. Now my main result is a combinatorial construction of high-dimensional expander families of all dimensions, such that the k-dimensional up-down walk has spectral gap at least 1 over 1 plus log h times k plus 2 times k plus 1. So this is a modification of the LMY construction, where I'll in fact leave the faces of LMY unchanged and only introduce a new weight function. But it turns out that this weight function is enough to give this exponential improvement in the spectral gap. So LMY had a spectral gap for the k-dimensional up-down walk of around 1 over k2 to the k. Now, if h is very large and k is very small, that still could be better than our bound. But as long as k is decently large, we have a roughly quadratic dependence on k in the denominator, whereas they have an exponential dependence on k. So we do get an exponential improvement in the spectral gap. Of course, this quadratic dependence is still not optimal. The optimal is on the order of 1 over k. Now, to present the construction, the starting point is an expander graph. So you may recall an expander graph is a graph where the random walk mixes rapidly. So this will rapidly approach the uniform stationary distribution. The inputs to the LMY construction are an expander graph G and a dimension H. Now, the graph G does not have to be an expander, but we'll typically choose it from an infinite family of expanders, while we hold H as a constant. Then, as I mentioned, this is going to look like a graph product. So our vertex set will naturally be the product of the vertices of G with a set of order H. And we'll think of the set of order H as being, say, the vertices of a complete simplicial complex. But really what this is going to look like is we had our graph G, we replace every vertex in G with a set of size order H, or with a cluster of vertices of size order H. Now for the k-dimensional faces, L and Y let these be all sets of k plus 1 vertices contained in at most 2 adjacent clusters with disjoint subsets across the clusters. So what that means, here I've shown an example of a 2-dimensional face. As you can see, there's these 3 red vertices contained in 2 adjacent clusters, and the sets are disjoint across the clusters. So that means that since we have, say, this red vertex and this red vertex, we could not have this vertex here or this vertex here in the simplicial complex or in the face. But that's okay because we've instead chosen to have this vertex in the face. Just to make sure that makes sense, here's an example of a 3-dimensional face, and here's another 3-dimensional face. Now L and Y, recall that we need a weight function. L and Y just chose the uniform weight function. So weight 1 for all h-dimensional faces. Now let's look at the up-down walk on this construction. Here I'll illustrate the 4-dimensional case. So we started a 4-dimensional face consisting of 5 vertices, and we repeatedly add and pop vertex. So add and pop. Here we have all our vertices in one cluster, so we can now move on to any adjacent cluster. And that's what we've done. We moved on to this cluster, and we just continue adding and popping. And you can see what happened. We basically performed an amoeba-like walk on the underlying graph G. So intuitively, if our underlying graph is a good expander, then for any constant k, this up-down walk is also going to mix rapidly, because we're essentially doing a random walk on the underlying graph. There is a slowdown because we need to get all vertices, all k plus 1 vertices from one cluster to another, but the slowdown only depends on k, so if k is a constant, it's a constant slowdown. And this is really the main intuition behind the L and Y construction. Now let's look more closely at the dependence on k. So let's start at this red face, this red 4-dimensional face, and look at the up step. So here we add one of the blue vertices, all with equal probability. So we're equally likely to add to either cluster. Let's say we add this one. Now we need to do a down step, so we remove a red vertex. But we're more likely to remove from this cluster because there's more vertices here. So say we remove this vertex. Now you can see what's happening. The probabilities in the up-down walk are skewed towards having vertices evenly split between 2 adjacent clusters. Because in the up step, we're equally likely to add to either cluster, and the down step, we're more likely to remove from the larger cluster. We can also think of this as a random walk on a hypercube. So we assign one cluster with the label 0, the other cluster with the label 1, and now we have, at any given time, we may have k plus 2 vertices after an up step. And in the up-down walk, we repeatedly choose a vertex, and of course replace it with a new vertex in either cluster. So we're just doing a random walk on this hypercube. And the only way out of these clusters is to get all vertices in one cluster or the other, which corresponds to all zeros or all ones vector. Now on average, it's going to take an exponential amount of time for a random walk on this hypercube to reach just one of these only 2 vectors. And this means that we'll get an exponential mixing time, at least intuitively, with respect to k, for the kth order up-down walk on the LMY construction. And indeed, this exactly plays out, and the best known bound for the up-down walk spectral gap has an exponential dependence on k for the LMY construction. Now to see how we're going to improve this, we can take another perspective we create this new graph shown here on the right by replacing each edge in the original graph with a length k plus 1 path. Now we can project the k-dimensional faces from the LMY construction down to vertices of this new graph. For instance, here we have a three-dimensional face with 3 vertices up here and 1 red vertex down here. That projects to this red vertex on the right. That's 3 steps away from this one down here and 1 step away from this one up here. Then we can project every k-dimensional face down, so we can in fact project the k-dimensional up-down walk down to this graph on the right. And here's what that looks like. So on the left, we're doing the up-down walk. On the right, we have the projection. And it's going to project down to a random walk on this graph on the right. But it's crucially going to be a random walk with directed edge weights, such that the mixing time within each of these length k paths is on the order of 2 to the k. It's going to be exponential in k. So the edge weights are going to ensure that. That was the intuition we saw with the hypercube. So my approach to improving the LMY construction is to adjust the weights of faces so that the associated projected random walk on this graph has just uniform undirected edge weights. So if instead of having these strange weightings that induce an exponential mixing time within each length k path, if we had, say, unweighted paths, this would have a quadratic mixing time in terms of k. And that would therefore, at least intuitively, replace the exponential dependence on k in the spectral gap with a quadratic dependence. And so this is exactly what I'll do. So formally, the weight function I'll define is to let an h-dimensional face sigma with j vertices in one cluster and h plus 1 minus j vertices in another cluster have weight j minus 1 factorial times h minus j factorial. So you recall that the LMY construction had uniform weights, so they would have had weight 1. And a nice thing about this is that this is an integer, so we can actually view this as an unweighted simplicial complex, but with multiplicity given by this expression. And then I'll show that with this weight function, on the faces of the LMY construction, for an underlying graph G, the kth order up-down walk has spectral gap at least the spectral gap of G over around k squared log h. So again, as long as k isn't too small, this is an exponential improvement over the LMY construction. And recall that since G will be chosen from a family of expanders, this numerator here, the spectral gap of G, is bounded below by a constant. So now to wrap up, in summary, we obtain exponential improvement in the up-down walk spectral gap of the LMY construction, but it is still quadratically worse than optimal. Now, some algebraic constructions do achieve the optimal spectral gap of on the order of 1 over k, but our combinatorial construction is much more elementary. And so it's natural to ask, well, can any combinatorial construction do better? Can we close this gap between the order 1 over k squared, approximately, spectral gap of our construction, and the optimal order 1 over k? Now, I think this is a very interesting question. It does seem like we hit an impediment when trying to improve our construction shown here. So I've given more details of this in the paper, which you can find online. But it really seems that, for instance, an additional modification to the weight function would not be sufficient to close this gap between the quadratic and linear spectral gaps. It really seems like we're going to need some new ideas. So that's it. Thanks for listening.